Hi students, I am Praveen Sebastian Paul. In this lecture we are discussing an NPN type transistor. So as we mentioned in the earlier lecture, a bipolar junction transistor, that is a BJT, is a type of transistor that uses both electrons and electron hole as charge carriers, and a bipolar junction transistor allow a small current injected at one of its terminal to control a much larger current flowing between the two other terminals, making the device capable of amplification purpose or a switching purpose. And basically these transistors are classified into two types. They are NPN transistor and PNP transistor based upon the mode of constructing this type of transistor. And in this lecture we are discussing what is an NPN type transistor. When a single P-type semiconductor layer is sandwiched between two N-type semiconductor layer, an NPN transistor is formed. The circuit symbol and the diode analog of the transistor is shown in this figure. And in this figure it is shown that the electric current always flow from a P region to an N region. The NPN transistor is made up of three semiconductor layers, one P semiconductor layer and two N-type semiconductor layer. The P-type semiconductor layer is sandwiched between two N-type semiconductor layer. The NPN transistor has three terminals. They are emitter, base and collector. The emitter terminal is connected to the left side of the N-type layer. The collector terminal is connected to the right side of the N-type layer. The base terminal is connected to the P-type layer. The NPN transistor has two PN junctions. One junction is formed between the emitter and the base, and this junction is called the emitter-base junction or emitter junction. The other junction is formed between the base and the collector, and this junction is called the collector-base junction or simply the collector junction. We know that the doping is the process of adding impurity to the intrinsic semiconductor to improve its electrical conductivity. The electrical conductivity of the semiconductor is depending on the doping level added to it. If the semiconductor material is heavily doped, its electrical conductivity is very high. That means the heavily doped semiconductor material has a large number of charge carriers which conduct electric current. If the semiconductor material is lightly doped, its electrical conductivity is very low. That means the lightly doped semiconductor material has a small number of charge carriers which conduct electric current. We know that the N-type semiconductor, the free electrons are the majority charge carrier and holes are the minority charge carrier. In an NPN transistor, the left side N region, that is the emitter region, is heavily doped, and so the emitter has the large number of free electrons. And in the P-type semiconductor, the holes are the majority charge carrier and free electrons are the minority charge carriers. The P region, that is the base region, is lightly doped, so the base has a small number of holes. The right side N region, that is the collector region, is moderately doped. Its doping level lies between that of emitter and base. When the atom loses or donates an electron, it becomes a positive ion. On the other hand, when an atom gains or accepts electron, it becomes negative ion. The atoms which donate electrons are known as donors, and the atoms which accept the electrons are known as acceptors. So these are the basic principles of an NPN transistor. When it comes to the working of an unbiased NPN transistor, when no voltage is applied to a transistor, it is said to be an unbiased transistor. At the left side region, that is the emitter region, and the right side region, that is the collector region, the free electrons are the majority carriers and the holes are the minority carrier, whereas in the P region, that is the base region, holes are the majority carrier and the free electrons are the minority carrier. We know that the charge carrier always try to move from higher concentration to a lower concentration region. For free electrons, N region is higher concentration region and P region is lower concentration region. Similarly, for holes, P region is higher concentration region and N region is lower concentration region. Therefore, the free electrons at the left side, that is the emitter region, and the right side N region, that is a collector region, experiences a repulsive force from each other. As a result, the free electrons at the left side and the right side N region will move into the P region, that is a base region. During this process, the free electron meet the hole in the P region near the junction and fill them. As a result, the depletion layer is formed at the emitter to the base junction and base to the collector junction. At emitter to the base junction, the depletion region is penetrated more towards the base side. Similarly, at base to collector junction, the depletion region is penetrated more towards the base side. This is because at emitter to base junction, the emitter is heavily doped and base is lightly doped. So the depletion region is penetrated more towards the base side and less towards the emitter side. Similarly, at base to collector junction, the collector is heavily doped and the base is lightly doped, so the depletion region is penetrated more towards the base side and less towards the collector side. The collector region is lightly doped than the emitter region, so the depletion layer width at the collector side is more than the depletion layer width at the emitter side. So when we are analyzing each of these junctions, firstly we are considering the emitter-base junction. Let us assume that at left side N region, that is the emitter region, each atom has 3 free electrons, and at the P region, each atom has 1 hole. During the diffusion process, the free electron move from the emitter to the base. Similarly, the hole move from the base to the emitter. At emitter-base junction, when the N region, that is a emitter atom, meets the P region, that is a base atom, each N region atom donate 3 free electrons to the 3 P region atom. As a result, the N region atom which donates the 3 free electrons will become a positive ion, and the 3 P region base atom which accepts these 3 free electrons will become negative ion. Thus, each N region positive ion produces 3 P region negative ion. Therefore, the depletion region at the emitter-base junction contain more negative ion than the positive ions. The negative ions reside at the P region near the junction, and the positive ion resides at the N region near the junction. Therefore, the depletion region is penetrated more towards the P region. That is, it is penetrating towards the base region than the emitter region. When it comes to the base collector junction, let us assume that the right side region, that is a collector region, each atom has 2 free electrons, and at P region, each atom has 1 hole. During the diffusion process, the free electron move from the collector to the base region. Similarly, the hole will move from the base region to the collector region. At a base collector junction, when the N region, that is a collector region atom, meets the P region, that is a base atom, each collector atom donate 2 free electrons to the P region, that is a base region atom. As a result, the collector atom which donates 2 free electrons will become a positive ion, and the 2 P region base atom which accepts those 2 free electrons will become negative ion. Thus, each N region positive ion produces 2 P region negative ions. Therefore, the depletion region at the base collector junction contains more negative ion than the positive ion. The negative ion resides at the P region area, that is the base region near the junction, and the positive ion resides at the N region, that is a collector region near the junction. Therefore, the depletion region is penetrated more towards the P region than the N region. However, the depletion layer width at the collector side is more than the depletion layer width at the emitter side. This is because the collector region is lightly doped than the emitter region. So my dear students, these are the basic concepts of an NPN transistor, and we had discussed about the unbiased condition of an NPN transistor. So dear students, hope you had understood this topic. So my dear students, kindly write down this assignment question. Our question is, write notes on NPN transistor and the working condition of a unbiased NPN transistor. So dear students, see you soon. In the upcoming lecture, we will discuss the working of a biased NPN transistor. So dear students, see you soon. Until then, goodbye, thank you, and all the best.